Let's do a few more examples of improper integrals type 2. So looking at the next example in our packet, what you might notice is that starting off, and this is something to look for, say, on the exam, because there will be improper integrals on the exam. And what you want to look for is, well, is there a discontinuity, or is there a problem with the boundaries? So looking at x minus 1, we know that, well, first of all, if there were a negative in there, that would be a problem because it would be not real. But also, dividing by 0 is another problem. And if x is equal to 1, again, that would be undefined. So any undefined value, any vertical asymptote or whatever, is something to see. So basically, before I start solving this is a problem. The fact that we're integrating all the way up until 1, which would amount to, in this case, a vertical asymptote on the graph. So again, what I need to do is I need to extract that as a limit, just like with a type 1 integral, and this would be the limit as t approaches 1. Again, from the right, since it's on the bottom. If it was on the top, you need to take the limit towards that number from the left instead. And again, I'm just going to change 1 to t. And so I'm imagining taking, instead of evaluating to 1, because I'm not allowed to, because it's discontinuous, I need to instead take the limit and see what happens as I inch my way closer and closer to that position. And otherwise, from here, we're just going to be solving this limit. And here we could, technically you could skip the u sub, but let's just do a quick u sub because it's quite easy. But if we wanted to know the antiderivative, I could sub in u equal x minus 1, which would mean du is directly dx. And I could change this integral from terms of x to terms of u. Another thing you might be wondering is if you do u sub, do I need to change t? But no, with t, that's going to be left alone. But if I do plug in the boundaries, I do need to change these since these were originally x in terms of u. And if x is equal to t, then u would be t minus 1. And if x is 5, then u would be 4. And then this would leave me with 2. Well, again, I could pass the 2 through both the integral and the limit, and this would leave me with 1 over the square root of u. And dx is directly equal to du. And so what I'm left with is a pretty simple antiderivative, u to the minus 1/2 power. And again, I could rewrite it as such. Let me just do that, not so I don't have to rewrite the whole thing, but u to the negative 1/2 power. And by power rule, I could add 1, which would be positive 1/2, and drop the reciprocal 2. So this would leave me with 4, the limit as t approaches 1 from the right, of u to the positive 1/2, or again, that's equal to the square root of u. Let's just leave it at that. Evaluated from 4 to t minus 1. Now, plugging in my boundaries, again, because in order to figure this out, I need to plug in my boundaries so I can try to figure out my limit. I'm going to be left with 4 times the limit as t approaches 1 from the right. The square root of 4, which is, of course, 2, minus the square root of t minus 1. And now, of course, what I need to do is figure out the limit. So the limit of a constant is, of course, a constant. And now what I'm looking at is the limit as t approaches 1 from the right of t minus 1. But, this is something where if this limit is 0. And again, the right-hand limit is very important. If there was not a right-handed limit, this limit would not exist. So things you need to be careful about. But, the graph of t minus 1 the graph of a square root will always kind of come down towards 0 as you get very, very close to 0. But, if I were to plug in 1, technically this would be 0. So it's continuous all the way up until 1. Ergo, I can plug in 1. What I end up with is 0 as my limit, since it is right-sided limit. But ultimately, what I'm going to be left with is 4 times 2 minus 0, or 4 times 2, which is, of course, 8. And this will give me the area of my improper integral. And before we move on, let's just take a peek at what this function looks like so we can get a sense of this. But again, what we'd say is this is a convergent portion of area. So this converges. Whereas the previous example in the previous video was divergent. And again, some improper integrals converge, some diverge. It just depends. You got to do the math to try to figure it out. So if we take a peek at our graph here, let's just graph the original function, 2 divided by the square root of x minus 1. Our window is a little bit messed up from before, but we really just care about this from 1 to 5. So let's graph it from 0 to 6 and say negative 5 to 10, or whoops, I want to leave the scale alone, from negative 5 to 5. Just using some random numbers to sort of visualize what's happening from 1 to 5. But from 1 to 5 on this graph, again, we knew it has a vertical asymptote out of 1. And so we're sort of seeing, does this area add up to something finite? And if we were to say, take our window from, I don't know, 0 to 100 and look at it, we could get another better look at this. Well, on the calculator, it appears to cut it off, which again is not truly what will happen with this function, but so not. Calculators, again, we should not trust them over other things, other properties that we know about the function. But anyways, what we've concluded is that the area from 1 to 5 in here is equal to exactly 8. Again, the math shows this. And how we could kind of imagine is, well, even if you keep going and going, it will never exceed 8. It may get closer. You know, technically, you can't go to infinity. That's the issue with infinity. But we can get closer and closer to 1 and see that the pattern, see what happens to that particular pattern.